Well, good morning. We're going to do chapter 7 today that deals with aqueous solutions. But before we do that, let's look at the lab we're going to do on Wednesday. This is lab number 8, and it allows us to determine an empirical formula. What we're going to do is basically burn magnesium ribbon. When we do this, we're adding oxygen to the magnesium. We will measure the mass of the oxygen. We know the mass of the magnesium we start with, and we can determine the mole ratio. Remember, empirical formula is basically the simplest formula for a compound. Lowest whole number ratio of the elements in a compound. It's a mole ratio, basically. For something like glucose, we have 6 carbons, 12 hydrogens, 6 oxygens. You divide all of these subscripts by the smallest. When you do that, you get CH2O. Okay. Empirical formula is what you get when you do a chemical analysis. It doesn't tell you much about the compound unless you know something else about it. For instance, this is acetic acid. It also has an empirical formula of CH2O. When we talked about this back in chapter 3, I think, we looked at this little video. It's so neat we can do it again. If you take sugar, glucose, add concentrated sulfuric acid very, very carefully. The sulfuric acid will catalyze a decomposition, giving us simply carbon and water. That's where the term carbohydrate comes from. The empirical formula is 1 carbon, 1 water, carbohydrate. After a few minutes, it starts to turn ugly, brown, and then you get this column of pure carbon coming out the top. The water slough to steam. It's a very exothermic reaction. Kind of really neat. All right. What we're going to do is, like I said, react magnesium metal with oxygen in the air. We will take the mass of the magnesium metal. Mass divided by molar mass gives us moles of magnesium. We will add the oxygen to the magnesium. Take the mass of this little ribbon when it's done. Subtract it. That will give us the mass of oxygen. Again, mass divided by molar mass. So we know moles of magnesium and moles of oxygen. All right, we're going to start off with a length of magnesium ribbon. What you're going to do is roll this around a pencil or a little finger or something until you get something like this. You're going to place it in a crucible, and we're going to heat the heck out of this crucible. Going to heat it so it's red hot. When it hits a certain temperature, the magnesium will catch fire. Very important that you wear safety glasses. Don't stare at the thing because it's very bright. When you're done, you're left with this white powder in the bottom, and again, everything is red hot. So you have to be very, very careful with this. All right, so we know the moles of magnesium. We calculate that by doing the subtraction. That gives us the mass. Mass divided by molar mass gives us moles. Let's just pretend that we did this, and X here was 0.015. I just made that up. Okay? Oxygen, the same thing. We do the subtraction. That gives us the mass of oxygen, mass over molar mass. That gives us Y, the moles of oxygen. And again, I made that up. So, our empirical formula right now looks like this. MgXOY. And these are the numbers that we just put in. Now, mole ratio expressed in closest integers. These are obviously not integers. So like I said earlier, you take the smallest, divide them both by the smallest. This is 1, of course, and this is a little over 1. So our empirical formula now looks like this. But again, to get an integer, you change this to 1, which we don't show, and we would write the answer as MgO. Simple, right? And it's fun. So take a look at the procedure before you come. Again, be very careful because things are literally red hot. All right, if we're going to talk about aqueous solutions, the first thing we need to talk about is water. Water is a remarkable compound. When we talked about bonding, we said there were 2 basic types. Covalent, where we share electrons between the atoms, and ionic, where we totally transfer the electron. Well, in reality, these represent limits. Most bonding is somewhere in between these limits. To make a covalent bond between 2 chlorines, we would take one with our 7 electrons, bring in the second. This gives us 8 electrons around each of the chlorine atoms, and we show that with our dash. Now, between 2 identical atoms, the sharing is essentially perfect. But if you have different atoms here, it will not be. We will show that by looking at 2 examples. This is hydrogen, H2. They're both identical. And this is hydrogen fluoride. They're not identical. What we're going to do is use what's called an electrostatic potential map to show this. Now, an electrostatic potential map is, you can describe it as showing electron distribution. That's not really exactly what it is, but that's close enough. Let's start with hydrogen. For hydrogen, the way we calculate the electrostatic potential map is we tell our computer we have these 2 hydrogen atoms so far apart. And we have a total of 2 electrons. We then start calculating where those electrons are. We do this in 3D space and go out until we encompass roughly 90% of the electrons. So, calculations tell us that somewhere in this space, 90% of the electrons live. We then tell the computer to take a point and move it around the surface. And as it does, measure the electron density. And then you color it. You color it. For hydrogen, it looks like, maybe a line. Okay? It's more or less a sphere, and the color is uniform. This tells us that the distribution between the 2 identical atoms is the same. Okay, let's do HF. We're going to do the same procedure. Step 1, calculate where the electrons are. We get a slightly different shape this time. Step 2, we're going to calculate the electron density along this surface. what we wind up when we do that is a really cute looking Easter egg. We have one region of the molecule that's dark blue, one region of the surface here that's red. Now, when we color these, blue represents the lack of electrons, electron deficiency, or a positive charge. Red shows a negative charge, excess electrons. So what's happening here is that fluorine is pulling the electrons away from the hydrogen towards itself. Again, this is hydrogen, looks like a lime, looks like an Easter egg. This is what's called a polar covalent bond. Polar covalent bond you can show using a dipole moment. That's basically an arrow with a plus on one end. This shows the positive end of the molecule. This shows the negative. All right, why does this happen? It's a phenomenon called electronegativity. Electronegativity is something that's inherent in every atom. Every element has its own electronegativity. The lowest are down in this corner of the periodic table, and the highest is up here. Fluorine is the highest at just about 4. Hydrogen's over here at 2.2. Fluorine has the inherent ability to attract electrons in a covalent bond towards itself. All right, so much for hydrogen and HF. We're talking about water, aren't we? Water has hydrogen and oxygen. Oxygen is 3.44, much more electronegative than the hydrogen. So, we would predict that the covalent bond between hydrogen and oxygen is also polar. Let's start off with our Lewis structure for water. We look at our periodic table. Oxygen is group 6, 6 valence electrons. Hydrogen is group 1, 1 valence electron. We will pair up the unpaired electrons. We convert this to little dashes, and this is our Lewis structure for water. Now, there's a theory referred to as the valence shell electron repulsion theory that tells us the geometry of molecules. We're not going to talk very much about that. It's more or less a general chemistry thing. But according to VSPER, water has a geometry that's bent. This is what it is, valence shell electron repulsion theory, VSEPR. What it says is you count the number of things surrounding the oxygen, the central atom. Things being electrons in either unshared pairs or bonds. The logic is these electrons are going to repel each other and get as far away from each other as they can. We can see this by watching this little video. If we had a central atom here with 2 lobes of electrons, now these could be bonds, whatever, we get linear geometry, 180 degrees. If we bring in a third, we get trigonal, 120 degree angles. And when we bring in our fourth, like we do with water, we get tetrahedral with 109.5. This is the geometry of water. Water is therefore bent. That's the official word for it. All right. Remember we said there's a difference in electronegativity between the hydrogen and the oxygen. That means that each of these bonds are going to be polar. So we have a dipole here and a dipole here. Now, because water is bent, that means that one side of this molecule is going to be electron deficient, and the oxygen is going to be electron rich. The electrostatic potential map is going to show us the geometry of the electron density around the oxygen. And it looks something like this. Oh, here's our dipole, our molecular dipole. This end of the molecule is positive, and the oxygen will be negative. If you look at the electrostatic potential map, we have a nice big blue bottom, with 2 hydrogens, and a big red oxygen. Our molecular dipole runs up this way. This is water. This is the thing that makes water so special. It has this tremendous molecular dipole. We will see that this molecular dipole is what allows water to dissolve ionic compounds, and basically is what makes water essential for life as we know it. Water is the best substance we know of for doing this. All right, let's show this by taking a cube of sodium chloride, and we're going to animate this surface dissolving in water. When I click the magic button here, water molecules will come in, remove an ion from the surface, and carry it away. Pay attention. Here we go. There goes a sodium. There goes a chlorine. Another chlorine. Another sodium. And blah, 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 until it's all done. But if you were paying attention, and I hope you were, I hope you noticed that the way water removed the ions from the surface was different if we had the cation or the anion. For the anion, if you noticed, the waters were all oriented with the hydrogens pointing towards a negative charge. That's because this is the positive end of the molecule. Something like this. There's a negative charge, here's the positive end of the molecule. For the sodium cation, the negative end of the molecule is pointing towards the charge. Here's the negative, this is our positive. Now, why is that important? Basically because when water surrounds the charge like this, what it does is distribute the charge. Nature doesn't like a charge just sitting there by itself. If you spread it out enough, though, it can be very stable. We can show this, again, using electrostatic potential maps. This represents our sodium cation. The blue is associated with the positive charge. I have placed 3 water molecules around it with the negative ends pointing in. What I'm going to do next is tell my computer to take this entire cluster and calculate electron density and then color it. What we get is something like this. Remember, our big blue ball is right here, and it's gone. We instead have distributed this charge over these three water molecules, and everybody is delightfully green. But water doesn't live in groups of 3. It lives mostly in groups of 8 to 10. So we'll see what happens when we expand this to 8 water molecules. But first, let's just do a little bit of nomenclature here. Substance dissolved, it's called soluble. Solubility is the amount of a substance. If we take magnesium carbonate in water, 25 degrees, 298 Kelvin, the solubility is 0.53 grams per liter. And that's how much you can possibly get in at room temperature. You can cheat. The maximum amount is called a saturated solution. Solvent is the thing doing the dissolving. Solute is the thing being dissolved. Now I said you could cheat. Remember, things are more soluble when the water's hot. You're going to make pasta. You dump in the salt in the water, heat it up, it goes in solution, right? So it's more soluble hot than cold. There are exceptions though. Sodium acetate is a substance that is very easy to make what's called a supersaturated solution. Supersaturated, you take sodium acetate, you put way too much in there. Heat it up, it'll go in solution anyway. Think of it, supersaturated, as this of fries. We supersize it, right? Okay. Nonetheless, we can put more in there than we're supposed to. If we let sodium acetate cool slowly, and you don't even look at it, you can wind up with a solution with way too much in there. This is a supersaturated solution of sodium acetate, and the neat thing is that as long as this isn't disturbed, it'll sit like that. Cool down to room temperature, it just stays that way. We're going to disturb this, however, by taking a single crystal of sodium acetate, dropping it down in the flask. It'll hit about here. The second it hits, you see the crystals start to form. And eventually this entire flask will set solid. It also gets quite hot. That's because we had to heat this up to get it in solution, right? When it comes out of solution, it gives all that heat back up. Kind of a neat way to store energy, actually. Any questions? All right. What is soluble in what? It's a very simple rule of thumb. Like dissolves like. When we're speaking of like and not like, we're speaking of polarity. We just saw that water is a very polar solvent. Things that are polar will dissolve in water. Ionic compounds, for example, dissolve in water. This is alcohol being added to water. Alcohol has a carbon chain, but there's OH on it. The hydroxyl group is polar, just like the one in water. And so this goes in. You can add as much alcohol as you want. It's miscible in all proportions. That means you can just keep adding until it's almost all alcohol. If, however, you take something that is non-polar, this is olive oil being added to water. And if you've ever made salad dressing, you add it, you get these bubbles, they don't mix. You have to shake the heck out of it just to get a suspension. Oil is very nonpolar, very insoluble. Simple rule is polar things dissolve in polar solvents. Nonpolar things will dissolve in nonpolar solvents. Simple rule of thumb. Now, when things dissolve in a polar solvent, ionic compounds, for example, we saw that they form ions. These ions in water have the unique property that they allow an electric current to flow through the water. If there were no ions in water, it would be an insulator, pure water. We'll see later it's not. But things that conduct an electric current are referred to as electrolytes. Things that do not are non-electrolytes. Now, when I was a child, we used to test for electrolytes and non-electrolytes using something like this. We would have the beaker with our stuff in it. We would have 2 plates from either side of the power source and a light bulb. If we had ions, the light bulb would light. It would conduct electricity. Now, when I was young, in general chemistry, they weren't quite as concerned with safety as they are today. So our power source here was basically plugged into the wall. Think about that. There's 110 volts here in water with ions. No, you touch it, you're fried. You can't take a shower with a hairdryer, can you? No. Okay. So this is how we used to do it. If we have a non-electrolyte, no ions, no light. If we have ions, the ions conduct the electricity back and forth, nice big light, and there's always an in-between, isn't there? This is a weak electrolyte. Weak electrolyte partially dissociates and conducts to a small extent. An example, this is acetic acid. Acetic acid dissolves in water to give acetate and proton, but unlike sodium chloride, where this is 100% ions, this is about 100,000 of these for every one of these. So it's a weak electrolyte. In general chemistry, you will get to know acetic acid and acetate. It's the classic example of a weak electrolyte. You will do calculations until you can't stand them anymore, I assure you. Today, we are much better at doing this. We use little battery-operated things with a scale that lights up. Electrolyte gives a big number. A non-electrolyte gives a weak electrolyte gives a smaller number, and a non-electrolyte, just in pure water, gives a fairly, very small number. When we hit chapter 8, we will understand why this isn't 0. The bottom line on this, if you have ions, it's an electrolyte. If you have few ions, it's weak. No ions, it's a non. Sugar dissolves in water nicely, but it does not form ions. So it's a non-electrolyte. Any questions? All right, so much for water itself. What can we do with solutions? Well, there are lots and lots of reactions that happen in water. If we know the concentration of our ions in water, we can do calculations. This is the concept of molarity. Molarity is simply defined as the number of moles of a substance divided by the liters of our solution. Number of moles and our volume, always in liters. Molarity. For example, this is a volumetric flask. In a volumetric flask, there is a little tiny line that's etched. This is a 1 liter flask. If you fill this all the way up to this tiny line, exactly on it, we have 1 liter of solution. Volumetric flask. They're expensive because you have to do this by hand. All right, if we put something in this, for example, 1 mole, we have 1 mole in a liter. It's a 1 molar solution. That's a joke. All right, let's talk about how we really do this. Molarity. The abbreviation is an uppercase M. That's again important because in general chemistry you will meet molality, which is slightly different. And it's abbreviated with a lowercase m. So remember, uppercase is what you want. To make our solution, we start off with our volumetric flask. Remember, molarity is going to be moles over volume in liters. First thing we do is we weigh out some substance so we know the number of moles. And we're going to put it in our flask. So we know how many moles this stuff is. We weigh it. Next, we're going to add water until we hit the 1 liter mark. We now know how many moles we put in, and we know our volume in liters. Simple concept, isn't it? But this will allow us, again, to do calculations of solutions of ions. Let's do a simple calculation. We take 3.25 grams of sodium bromide. We have 1,250 mils of solution. Calculate the molarity. Now, we know a mass, and we know the molar mass of sodium bromide. We need to know the number of moles in our solution, right? To calculate the molarity, we need moles of sodium bromide and our volume in liters. If we know a mass and a molar mass, how do we get moles? Mass divided by molar mass is moles. All right, we need to divide this by the number of liters. This is milliliters, so we divide it by 1,000. 3.25 divided by 1.02 divided by 1.25 would give us the answer. Let's think for a second about the units. Grams are going to cancel. We have mole here to the -1, but it's in the denominator. So what we really have is 1 over mole, right? When you have a reciprocal of a reciprocal, what do you get? Turn it upside down twice, you get the thing. That means this mole per mole comes up as mole. All right, do our calculation. 3.25, 102, 1.25. We get 0.025 moles over liters. That's molar. Now, depending upon which textbook you're looking at, this can be shown lots of different ways. Some people just use molar, M. Some people write this as italic, molar. Some people take the M and underline it and just stress that it is moles per liter. Some people use a script. These all mean exactly the same thing. Any questions? Let's do another one then. 6.47 grams of sodium acetate, 1450 mils. What's the molarity? Go ahead and set it up. We have a mass, we have a molar mass. Number of moles is going to be simply mass over molar mass. We have 1450 milliliters divided by 1,000, 1.45 liters. Going to cancel our grams. The per mole will come up top. 6.47 divided by 82 divided by 1.45. 0.05 moles per liter. Now, sometimes you'll see it written like this. Sometimes you will see it written as moles and liter minus 1, because you can do that on a word processor easier. Sometimes you will see it with the uppercase M, and that's preferred. Any questions? We have potassium hydrogen phosphate. This is its molar mass. We dissolve 238 grams of the solid in 275 mils. What's the molarity? This was actually an exam question. Once again, set it up. We have 238 grams. Our molar mass is 174. Moles is simply this. We have 275 milliliters divided by 1,000. That's 0.275. Grams will cancel. Per mole comes up top. 238 divided by 174 divided by 0.275, 0.4969. We have three significant figures here. It rounds to 497. Simple calculations, aren't they? Now, there are 3 tutorials that accompany this chapter. 15 points. Oh boy. This is the first one. Everybody loves this. Something like this will probably appear verbatim on your exam. Where do I get the questions? I hit new problem. That's it. In this, we have 3 blanks. 1 is missing. We are given a number of moles and a volume. What is the molarity? On your little card, if you don't remember it, moles divided by volume in liters, that's molarity. We know the number of moles, we know the number of liters. Moles divided by liters, 0.454. Everybody loves tables. Well, this one had molarity missing. Let's do another one. Here, volume is missing. Again, molarity is moles divided by volume, which means that volume is going to be moles divided by molarity. Moles divided by molarity gives volume. Here's our moles. Here's our molarity. Moles will cancel. And we get 4.26 liters. Our last one here. We're missing moles. We know a molarity and a volume. Go ahead and set this up. We're looking here for moles. Moles is going to be molarity multiplied by the volume. Molarity times volume is moles. Here's our molarity. Here's our volume. We have 0.365 moles. Here's another thing you can remember. You know how you always remember mass over molar mass. Here's another one. What we did here was we took a concentration, multiplied it by the volume in liters, and we got moles. That's worth remembering. Concentration times volume is moles. Mass over molar mass is moles. Useful things to know. All right. When you're working in lab and you're going to do a quantitative reaction, quite often you will have what's known as a stock solution of known concentration. And you will take and you'll add water to that or whatever to make your working concentration. Something like this. We have a solution that's 0.18 molar KCl. To do our reaction, we want 0.01 moles of KCl. What volume of our stock solution here do we need? Kind of like a real lab problem, right? Well, again, we know molarity is moles divided by volume. We're looking for volume here. Volume is going to be moles divided by molarity. Our number of moles, 0.01 moles per liter, or 0.01 moles. Our concentration here, 0.18 moles per liter. Moles cancel. Per liter comes up top. 0.01 divided by 0.18. 0.056 liters. In the lab, we typically measure in milliliters. So we would take our stock solution, pull out 56 mils, we would have 0.01 moles. Kind of a real lab problem. We can also get Avogadro involved here. Here we have a solution of sucrose. That's table sugar. C12H22O11. We have 300 mils of this, and the concentration is 2 moles. How many molecules is that? Well, let's remember, moles divided by volume is molarity. In order to find out how many molecules we have, we need to know how many moles we have, right? So we're simply solving for moles. Then, once we know the number of moles, Avogadro's number gives us molecules. So, moles is going to be equal to concentration times volume. We will take our concentration, we will take our volume, must be in liters, simply multiply these together, liters will cancel, and we get moles. So, we know how many moles of sucrose we have. We also know that 1 mole contains 6.02 times 10 to the 23rd molecules. Multiply this by Avogadro's number, moles cancel, and we get molecules. 2.26 times 10 to the 23rd molecules. Any questions? Well, we could do one more type of problem here. Actually, many more, but one more major one. And that involves mole ratios. Something like this. We have 2.5 molar potassium sulfate in this solution. How many moles of sulfate are in 150 mils? And how many moles of potassium are in the same volume? Well, we have a concentration and a volume. That gives us numbers of moles, right? When potassium sulfate dissolves in water, what happens? It's going to totally dissociate. Here we have water. Here we have potassium sulfate. We are going to put that in our water. Just like the sodium chloride dissolved, we're left with potassium ions that are free floating and sulfate that's free floating. the ratio, 2 potassiums for every sulfate. That's the mole ratio here, isn't it? 2 to 1. So, how many sulfates in 150 mils? How many potassiums? Going to be twice as many. Moles of potassium sulfate, concentration times volume. Liters cancel, and we get 0.38 moles of potassium sulfate. Now every potassium sulfate has 1 sulfate, right? There's our mole ratio. So we're going to take our mole ratio, the number of moles, simply multiply them, and we get the same concentration. 1 mole of sulfate for every potassium sulfate. For potassium, every potassium sulfate gives us 2 potassium ions. So here's our mole ratio, 2 times 0.38 divided by 1, twice as many potassiums as we had sulfates. Any questions? Well, the second tutorial in this chapter is mole mass relationships. It's a little more complicated than a table. You will switch between liters and milliliters, and I don't know, grams and milligrams, I think, also show up. We're looking for a volume. We have a concentration. We want 0.037 moles. So we're looking for a volume. Remember, moles divided by concentration is molarity. Moles divided by molarity is volume. We simply substitute. This is our number of moles. Here's our molarity. Do our division, and we get our answer, but it's in liters. We have to enter it in milliliters. Simply multiply by 1,666. So it looks more complicated, but it really isn't. Let's do another one. How many milligrams are there in 0.772 liters, 0.113 molar? We have methanol, and here's its molar mass. We are looking for a mass here, aren't we? We're going to convert that mass into milligrams. So, moles are going to be concentration times volume. Here's our concentration, here's our volume, here's our moles. We know the number of moles, and we know the molar mass of methanol. If we simply multiply those together, number of moles or grams per mole, moles would cancel, and we get 27.9 grams. Finally, the question for some reason wanted milligrams. 1,000 milligrams in every gram. Simply multiply by 1,000, 27,900. Any questions? Let's do one more then. Go ahead and look at this and think about how you're going to do this. We're looking for a volume, we have a concentration, we have a molar mass, and we want a certain number of moles. Remember to get volume, moles divided by moles per liter. We know our concentration, 1.75. We know the number of moles we want, we know weight. We're looking for 0.0502 liters. To get it to milliliters, you would simply multiply by 1,000, 50 mils. Now, the questions on Blackboard come straight from the tutorial, randomly. Any questions? All right, exam time. Real exam questions. Looking for the molarity. We have 10 grams of sodium hydroxide, 500 mils of solution. On the real exam, how do you do this? Well, we're looking for molarity. What is molarity? It's simply going to be moles divided by volume in liters. Moles of sodium hydroxide, 10 grams, 40 grams per mole. Substitute. Our grams would cancel. Mole would come up. We're at 0.5 molar. How many grams of calcium nitrate do we have to dissolve in water to make 500 mils of 1 molar solution? Again, this is a real lab question, isn't it? You want to make a stock solution that's 1 molar. How do you do that? Well, we're looking for mass here, aren't we? We know moles is going to be equal to concentration times volume. If we multiply our concentration, that's 1 mole per liter, and our volume, 500 mils, we get half a mole. If 1 mole weighs 164, how much does half a mole weigh? Simply multiply those together, and we get 82 grams of stuff. Any questions? Another one? This was an extra credit. We have a solution that was 0.375 moles per liter. We have a volume. How many moles is that? You can tell us an extra credit. because it's really easy, right? We know we're solving for moles, we have molarity, and we have a volume. Concentration times volume is moles. Take our concentration, multiply it by our volume. Liter and per liter cancel, and we have 1.78 moles. One more multiple choice. We have 200 mils of sodium chloride solution. We evaporate it, get this old crusty little beaker, weigh it. It's got 1.56 grams of solid. What was the molarity of the original solution? Our molarity is going to be moles of sodium chloride divided by our volume in liters. Moles of sodium chloride, 1.56 grams divided by 58 grams per mole. Grams cancel, moles comes up top. 1.56 divided by 58 divided by 0.2. 1.33 moles per liter. All right. The last part of this chapter deals with dilutions. There are two ways to do dilutions. You can take a solution of known concentration, add water to it, and calculate the new concentration. Or you could do what's called a serial dilution. Serial dilutions are very useful if you want to make a very, very dilute solution. So, a serial dilution, you start off with something. Let's pretend this is a liter. We will take 10 mils out, add it to 990 mils of water. That gives us 1 liter. We are down to our first solution. Take 10 mils of this, add it to 990. We get a liter. 10 mils. Do it again. Do it again. Down here at the bottom, our concentration is going to be very, very small. Let's see. This is the serial dilution method that's used to make homeopathic drugs. In this particular dilution scheme, if we started with 1 molar, every one of this would be 10 to the minus 2 of that concentration. So this is 1 molar, 1 times 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8 mole. Very dilute solution, right? Homeopathic drugs. This is the scheme that they use for dilution. FDA does not regulate these in general, although it has started to object to some. Because the concentrations are so incredibly low that it doesn't matter. It's just water. All right. This guy, strychnine. It's a poison. They made Aristotle eat it, right? He died. When I was young, you could go into any store, drugstore, and buy a little bottle of strychnine. It was great rat poison. Great if you were a little old lady trying to get rid of your husband. It was really good stuff, okay? But things have changed, right? You cannot go into Jewel-Osco and buy a bottle of strychnine anymore. Or can you? Actually, you can. There's a drug on the shelf in Jewel, I saw it the other day, called Cold Calm. Children's Cold Calm. Now, as parents, we all get upset with our children sometimes, right? Sometimes you think evil thoughts, give them strychnine. Well, you can. If you look at the ingredients here, these are belladonna alkaloids. This is a 6C dilution, less than 10 to the minus, I think it's 15 milligrams per tablet. 14 of those. Lethal dose is 0.2 milligrams. Very, very toxic stuff. This stuff, yellow jasmine, related to strychnine. Contact just with the plant can be fatal. 10 to the minus 12 of the starting sample. Nux vomica. That's a deep sounding name, right? That's strychnine tree. With this particular label, it was 10 to the minus 8 milligrams. Way, way less than the toxic dose. But this is one of the cases where FDA made them pull this from the market. They got it back on the market by cutting this in half. Now it's 10 to the minus 16 milligrams. So you can give your child strychnine, just not very much. All right. The other type of dilution, we have a solution of known concentration, we add water, and we get a new concentration. The thing to remember here, the thing to note, is that we take this known concentration, we dilute it, but the total number of moles doesn't change. You're just adding water. The volume changes, but not the number of moles. Now, how do we get numbers of moles? Concentration times volume. Our initial number of moles is going to be given by V1C1. Our final number of moles is given by V2C2. Now, since the number of moles does not change, these two are equal to each other. V1C1, V2C2. Total number of moles does not change. So, we have a known concentration, we add water, get a different volume, calculate the new concentration. That's all there is to it. We have sodium chloride at 0.53 molar, 500 mils, is diluted to a final volume of 1750 mils. What's the final concentration? Okay. Number of moles does not change. We calculate our number of moles with a concentration and a volume. We know a final volume. We're going to calculate the final concentration. V1, 0.5 liters. C1, 0.53 moles per liter. V2, 0.175 mils or liters, and we solve for C2. C2 is going to be these two divided by this guy. And our calculator, 0.5 times 0.5 divided by 1.75, 0.15 moles per liter. Initial concentration, final concentration, final volume, final concentration. Any questions? We have a solution that's 2.1 molar. We want to make 1,600 mils of 1.1 molar. What volume do we need? Once again, going to be a concentration times volume. We're simply solving for the initial volume. Go ahead and set it up. V1, C1, V2, C2. And we're solving for V1. V1, this is C1, this is V2, and this is C2. We're going to cancel moles per liter. 1.1 times 1.6 divided by 2.1. 0.84 liters or 840 milliliters. Any questions? Well, this brings us to the final tutorial for the chapter called dilutions. To what final volume? That's V2. We have to express it in mils. Should 140 mils of 2.3 molar volume concentration, and here's our final concentration. We're looking for the final volume, V2. So, V1, C1, C2, looking for V2. V2 is C1 V1 over C2. Plug it in, 0.58 liters. For some reason, the computer wants you to put that into milliliters. Simply multiply by 1,000. 580. Just remember V1, C1, V2, C2. Go ahead and set this one up. We are looking for C2. Here is V2, V1, C1. V1, C1, V2, C2. Remember, everything has to be in terms of liters. So 440 divided by 1,000.44. C2, C1, V1 over V2. Simple math. Do our substitution. 0.44. C2 or C1 is this. This is V2, C2. Simply, that's our math. 0.026 molar. Again, the questions on Blackboard will deal with standard dilutions here, not with serial dilutions. Any questions? All right, here's our list. Balancing, oxidation numbers, redox reactions, stoichiometry, mass ratios. Today, molarity 1 and 2, and dilutions. On Wednesday, remember, we will do the empirical formula. Please read it beforehand. Make sure you're up on it and be very, very careful. All right, have a good day.